All right, class, welcome to chapter 5, the last chapter of this book. We are getting ready for the end. So, indefinite integral is the name of this section, but what is that about, and what are we going to talk about in this last chapter 5? It turns out that we'll be going backwards. So we will be talking about something called integral calculus. And integral calculus is the opposite of what we talked about in the first 4 chapters, which are called the differential calculus. Differential calculus deals with finding derivatives, yes, and their applications. So, ever since chapter 1, we learned what a derivative is, right? It's the slope of the tangent line to a graph, which measures the instantaneous rate of change in the function, right? There's the function, where's that function heading at this point in time, right? Is it going down? Is it going down faster? Is it going up, right? So, how to find the derivative of a function and what is it good for, right? And also we looked at when the derivative is equal to 0, which means we had a maximum or a minimum possibly in the graph, and then we were able to solve optimization problems. Now, integral calculus is the reverse process to this. In other words, if we are, so basically in a differential calculus, we were giving you the function, right? And we are asking you to find the derivative. Now, in integral calculus, we start backwards. We know where the function's changing at a point in time. We know the rate of change. We know what the derivative of a function is at any point in time. Can we go back to find the function itself? So given the derivative, now, we will be asked to find the original function. Now, it turns out that this has its own set of really good, important applications, right? So that's what we are going to learn in this chapter 5. How do we use this and what sort of applications does it have? But again, remember, the important thing is that we will start with the derivative. So given the derivative, we are starting with a derivative, and we're going to want to find the original function. So how do we find that? Now, so this is now the reverse process to what we've learned so far. We will now begin. We will be given the derivative, right? So given the derivative, we will need to find the original function. This original function is called the antiderivative of the derivative. So the function itself is the antiderivative of its derivative. Yeah, so going back, again, given the derivative function, going backwards means to find the antiderivative. So we use, or we find, the name for it is a indefinite integral. That's the notation. So basically it's like, here's a function, find the derivative. All we had to do is put this little prime symbol, right, on f, and then you knew what you were asked to do. Now, what type of a notation do we use? So this is our notation, and we call this the integral of some function f of x. That's how we read this, the integral of f of x. And then we will always say this dx. We'll see where it comes from. We will see where this symbol even, why is this elongated S-looking shape? So we'll talk about this in actually 5.4. There's a section 5.3 that we're not really going to go over. I did post it online. It's really the calculus behind all of this. We don't really want to spend so much time on calculus. This being a business calculus class, we don't want to make things too complicated. As you saw, we're not really going over proofs, but we are just using the facts, right? Okay, so the integral, that's how we would read this. The integral of f of x dx is some other kind of function. And again, this f of x is the antiderivative, right? In other words, the original function. So just as I said here, where what? The derivative of this, right, is equal to the function in here. So this is the derivative. So taking the integral of the derivative gives you the original function. Okay, so we're starting with the derivative. And by writing the symbol, we are going back to the original function. All right. I think I've said that plenty of times already. Okay, so now what about this k? Why do I have another weird looking k there? By the way, that's called the constant of integration. So let me write that down as well. Okay. So to see what's happening with this k and the fact that we actually get a whole family of functions for an answer, not just a function, but a function plus some kind of a constant, let me just give you these possible answers. So what if f of x comes up, or that expression there comes up to be x squared plus 5? What would be its derivative? What would be the derivative of this function? So if I take the derivative of this function, I am going to get 2x, yes? What if I'm starting with this function? What is its derivative? Well, its derivative would be 2x. And I think you're getting my point that what? I don't know. Anything, any number, any constant. If I want to find its derivative, then I'm just going to get 2x. Why? Because the constant goes away. So basically what I'm saying is if I'm starting with an integral of f of x, where that's a 2x, yes? So if I want to find who or which one is the function whose derivative equals to 2x, right? So the derivative is 2x. Can you go back and find me the function? Well, it turns out right here are 3 examples of what that function f of x could be, yes? So this is exactly what I'm saying, is that your answer will be x squared. The derivative of x squared is indeed 2x. But it could be any other term that doesn't have an x right behind it, right? It could even be ln of 5, that's a number, or e to the 5th, that's a number. It doesn't have an x to it. So as you see, the antiderivative of a function is a whole family of functions, and that whole family of function is the variable part to it, plus any random constant k. So when finding the antiderivative of a function, or the integral, it's got 2 names, or antiderivative of a function, we must add a constant k to the answer. Okay? Because again, when taking the derivative of that k, it just disappears. All right. So, all right, let's move on and just talk about how are we going to find these antiderivatives? Well, there must be some formula. Same as we used formulas to find derivatives of functions, we're just going to have to use some formulas to find the antiderivatives of those functions. So here are the rules. Okay, now, which one was the most powerful rule when talking about derivatives? Sure enough, that was the power rule, yes? Now I want to talk about the power rule for integration. So it's really going backwards. Remember, when we talked about what was the power rule for derivatives, so x to some kind of power n, yes? When I took its derivative, what did we do? We brought the n up front, and then we lowered the exponent by 1, yes? Now, going backwards, when I find the antiderivative of something to a power, what do I have to do? Well, instead of lowering the exponent by 1, I have to bring it back up by 1, right? So we're going to increase the exponent by 1. And instead of dividing, right? Instead of multiplying by that exponent, I have to divide by that exponent. Okay, now I put here where n cannot equal to -1. It turns out that's something that we're going to have to pay attention to. And why did I say n cannot equal to -1? Because if this exponent is a -1 and then I divide by 1 more than it, what is -1 plus 1? Well, that would be a 0, yes? And we all know we cannot divide by 0. So this rule works for any power except for the power of not equal to -1. So if you have an integral of an x to the -1, you cannot use this rule. We'll see just at the bottom of this page what rule we're going to end up using. Okay, so it turns out that the same rules that applied for derivatives now apply for integration. So remember, when we took the derivative of a constant, whatever that, maybe we called it a c, or we kept it actually, okay, a constant times a function. So when I took the derivative of that, what did we do with the constant? We kept it, yes? And just moved on and concentrating on taking the derivative of the variable part, or the part that had a variable. So the same thing here. Taking the antiderivative, we just keep the constant. In other words, the coefficient, in this case, right? The constant that's multiplied to a variable part, it's called a coefficient. But we keep that coefficient, or that constant, and we just concentrate on taking the antiderivative of the variable part, right? So it's the same way. Now, sure enough, we had the derivative of a constant was simply 0, right? When, again, if your variable is called x, then the derivative of something that doesn't have an x is going to be a 0. The antiderivative of a constant, remember you actually have to go 1 in power. So really here, and I will show you, I could put this aside. So again, what is a k? Is an x to the power of 0? Yes. So there's 0 x's in there. So what we could use the top two rules to figure this out. So what do I do with a constant? If you have a constant inside of an integral, we keep it, yes? And just take care and move on to take the antiderivative of the variable part. Great. How do I take the antiderivative of an x to the 0? Well, the power rule says that what? What you have to do is you have to increase that exponent by 1. So increasing this exponent by 1 makes it an x to the power of 1. And then divide by that same power. Yes, so by this 1. So that's going to be a k, x to the 1 times divided by 1 is an x times k, that's a kx. And as always, don't forget you need to add another constant, which doesn't have to be this one. So now I kind of wish we would have used different k's for constants, but yes, it's not the same, right? So there you have it, why that rule applies. But sure enough, just like with all the rules that we have done, you're not going to go through all the steps in a bit. You're going to realize soon enough that the antiderivative of 5 is 5x, yes, same as you knew that the derivative of 5 is 0, okay? And last rule right here, same as what? When we took derivatives of sums of functions or differences of functions, what did we get to do when we took the derivative of a sum or a difference? That was the easy part. We simply went through and took the derivative of each one of them, right? So it gets distributed. The same thing. If you have a sum or a difference inside an integral, you just go term by term, right? Take the antiderivative of the first term plus or minus the antiderivative of the second term, and then that's how you move on. So again, going forwards or backwards has to be the same. Now remember what? Did the product rule come up so easily, or the quotient rule? So if you had, let's say, I'm just going to take this quickly on the side. So if you had the derivative of a product, were you allowed to just go and take the derivative of each one of them? No, right? That was not a rule. So it's going to be the same when you have a product inside an integral. You're not going to be allowed to just take the antiderivative of each of the factors. It doesn't work that way for derivatives either. And then the same thing for the quotient rule. So as a matter of fact, we're going to be dealing with this in the very last section of this chapter, which is 5.9. It's the integration by parts. It turns out it's really not that easy, okay? So we're going to learn how to use or deal with the product rule backwards. Quotient rule, we won't even deal with it. But of course, a quotient can always be looked at as a product. Yes, so maybe we could still use the product rule backwards or this integration by parts. But the point is, products and quotients, not so easy when we take the derivative, not so easy when we take the antiderivatives. However, sum and differences, yes, they behave nicely. All right, so I had said that before we even get to the bottom of this page, we will talk about this exception to the power rule. So what if we have a -1? What if our exponent here is a -1, right? So that's what we said. You can use this power rule if n is not -1. Now, what happens if this n is a -1? Then you would have to take the antiderivative of something that looks like this. Now, of course, at first, you will be very tempted to use the power rule backwards. You will forget. And immediately, when you use the power rule backwards, this says that what? You have to increase the power by 1, yes, and then divide by that power. So if you do that, you get an x to the 0 divided by 0, and which is 1 divided by 0, and this is undefined, yes? So that doesn't work. All right, well, if that doesn't work, what works? Well, let's rewrite this. X to the -1 is 1 over x, right? Do you agree with that? So obviously the answer is right here. But do you remember any function that we've talked about lately whose derivative looks like this? And there is a function whose derivative looks exactly like that, and that's the natural log function. So for this example, when we're dealing with an x to the -1 and we're thinking which function has a derivative that looks like 1 over x, the answer is ln of x. Now, the one thing we will still also have to do is, why do we put the absolute value, right? Why the absolute values? Okay. The absolute values are simply because, if you remember something else that I bothered you with a few sections ago in 3.2, when we talked about logarithmic functions, what's the domain of a logarithmic function? The domain of a logarithmic function is only positive values, yes? Can be inside a log. So, because of that, we need to make sure these x's might be positive, might be negative, we don't know. But when we take the antiderivative of it and we get that log, we do want to make sure those quantities turn out to be positive. And it can be shown in calculus. I'm not going to bother you with calculus, as I said, the real complicated examples, but it can be shown in calculus that ln of negative x, the derivative of that is 1 over x, and then ln of x, the derivative of that is also 1 over x. So because of that, we could make it positive or negative. In other words, we can take the ln of a positive or a negative, make it positive again, and we always get 1 over x. Okay, so I'm going to finish this video for now, and these are the rules. What we're going to do next is apply them.